Hello, my name is Bryant, and this is my Physics 2211 Black Hole and Orbits lab. So for this lab, we'll be going through the introduction and models, and then we'll talk about the experiment, which is entirely coding-based, and then we'll lead into discussion of the results and draw some conclusions. So for the introduction, the purpose of this experiment, this lab was split into two separate parts, the first of which having the aim of determining the mass of the black hole itself by assuming that the net force acting on the star orbiting the black hole is due solely to the black hole itself, while the second part of this lab involves finding the initial velocity of a spaceship as it does a figure-8 navigation around a planet-moon system in order to reach the planet without crashing. The entirety of this lab was coding-based. The relevant equations and concepts include Newton's second law, which essentially states that the net force acting on an object is equal to the mass times acceleration. Then we have the velocity update formula to the left. In the center, we have the position update formula, and to the right, we have the FNet formula broken down into its constituent parallel and perpendicular components, which will be discussed more in depth later. And then we have one more formula, the gravitational force formula, which is essentially the force of gravity equals gravity constant times the two masses over r squared. And then the preview of the experimental results for part 1 of the lab yielded an average black hole mass of 1.30544 e to the 34th. And since there were many values output by our code, we took the average of all the masses added together to find an average mass value that we can use and then for part 2, we were able to navigate the system without crashing using a process of trial and error. Granted, the motion ended up not being a figure-8. So to the left, we have an image from part 1 of running our code, and then to the right is the result of running our code for part 2. So in part 1, the arrows got bigger gradually as it approached the black hole due to the increased proximity to the center of mass of the black hole. And then to the right, we see this is not a figure-8 configuration, but it did not crash successfully. So here's the coding for part 1. We have our initial conditions, which include the gravitational constant here, and then the mass of the star, which is given to us, which is 2 times 10 to the 30th kilograms. And then to the right, we have all of essentially we're just applying all of the models that we discussed earlier, including like Newton's second law, for example. And then we have our coding for part 2. Oh, and for part 1, the system is the star and the surroundings are the black hole. And for part 2, we have our coding here, our initial conditions, which you can see to the left here. And then on the right, we have, again, all of our models applied. And the system is the spaceship, and the surroundings are the planet and moon. I have noted the ship's speed for the x value and the y value, which gives us our initial velocity. And then for the discussion, the spaceship didn't quite achieve a figure-8 orbit, but it succeeded to not crash and navigate the system as this was our primary goal. The initial velocity found in part 2 of the lab was found to be 2.45 e to the 4th, 2.45 e to the 4th, 0 meters per second. Potential errors arise from the possible impreciseness of velocities used that led to a non-figure-8 navigation. Part 1 gave us the average black hole mass through a series of iterations. However, a source of error may have come from the rounding of these iterations, which makes the final average of mass less accurate. And then to conclude our what if, the rate of change of momentum refers to an object's change in momentum, the product of mass and velocity over time, while net force refers to the sum of all forces acting on a system in particular point of time that either causes its motion or its resting state. The net force can be split into its constituent components, the FNet parallel and FNet perpendicular forces. The FNet parallel essentially changes the speed of an object, while the perpendicular component changes the direction of motion. And then for what does it mean? If we're determining the motion of the whole system, we have to account for the gravitational effects of every object in the system. And the black hole would have the dominant interactions due to its greater mass.